In this video, I'm going to continue talking about the Green Theorem. So this lecture, I'm going to focus more on the physical meaning of Green Theorem. Later on, I will give one more example to show you how to use the Green Theorem. So let's first do a recap of the Green Theorem. So if I'm giving you a 2D space, xy space with a closed region S, whose boundary is defined by C, and the boundary is defined in a counterclockwise direction, which means the boundary follows a counterclockwise direction such that the region S is on the left if I move along the direction of the boundary. Okay, if that's well defined, also I have two functions, f1xy and f2xy, and both these functions are continuous with respect to xy, and also the partial derivative, which means the partial f2 over partial x and partial f1 over partial y, they do exist and they are continuous. If that's the case, now the double integration of this form, which is partial f2 over partial x minus partial f1 over partial y over the region of S, is equal to the line integral of f over the boundaries. That's what the Green Theorem says. Okay. So one question is, what is the physical meaning of Green Theorem? Because if you look at this one, basically the Green Theorem talks about the divergence property. Is the divergence property of some vector field. I'll talk about it in more detail later on. So the reason we can consider this as a divergence property of some field, because if I look at this partial f1, partial f2, partial x minus partial f1 over partial y, it's sort of like the divergence for the two-dimensional field if we define the field properly. Okay, so if we define, if we define this f, this is a vector field, okay, which is different from the beginning. This is not the vector field. This is not the vector field we're going to define. Okay, the vector field is defined as f2xy and minus f1xy. So this is the vector field we're going to define. If we would define this vector field, and if we compute the divergence of that vector field, remember the divergence of the vector field is partial f1, which is the first component. This is my first component, f2 xy over partial x, plus this second component, which is partial negative f1 xy over partial y, and I compute it over here, which is exactly equal to partial f2x minus partial f2y. So here I drop the xy for simplicity. Okay, so this is exactly what's happening over here, which is exactly what's happening over here, right? Now, if I define the vector field like this, it looks like what this means is the integration of all this partial f2x minus partial f1y is integration of the divergence over the entire region. You can interpret this as accumulated divergence of region S. So this is what it means. Okay, the double integration means the accumulated divergence of S if we define the vector field as f2xy and minus f1xy. Okay, so let's take some physical meaning of that. Okay, if I look at that one, this one, if I define, let's say I use the orange color to represent the vector field that I draw based on this f vector over here. I can draw every point, I can draw a vector associated with that. Okay, remember the divergence means sort of how many, if I consider this vector field defines the velocity of the particles in the field. Now the divergence characterizes how many particles coming in versus how many particles coming out. Okay, so if divergence is positive, which means you have more particles coming out than the number of particles coming in. Okay, so the integration of that one, you basically for every point, I consider very, very tiny region and try to figure out, hey, how many particles coming in and how many particles coming out. you do all the different small tiny cells. Okay, if you do all the possible cells in the area, what's going to happen? You will see here that if I'm going to sit in the middle, right over here, for example, somewhere over here, not on the boundary, if any particle coming in will come from another small, very tiny cells, right? And whatever the particle will go to another cell. It never come out of this region, right? It only comes a region when you move on the boundaries. When you stay on the boundary, yeah, the particle will come out. Okay, so which means if I compute the accumulated divergence of S, which is given here, is the same as accumulated divergence only at the boundary. Only at the boundary. The reason because any inside point you cannot move at before you need to first move to the boundary, then you move out. That's why divergence for inside will cancel out. I'll emphasize over here. Divergence inside S, this region will be cancelled out. Because this property shows that accumulated divergence of S in the region S is the same as accumulated divergence only at the boundary. Okay, so that's the physical meaning of we do the next step. Okay, but let's go to the next step. So what is accumulated divergence at the boundary? We'll calculate that, right? So here's a demonstration of I calculated a very small divergence on a small portion of my boundary. Okay, so if you compute the accumulated divergence at the boundary, because that's the only thing I care about, because all inside will be cancelled out. So this becomes integration of, this is my still the field, right? This is still the vector, okay, field. So let's say, for example, I'm talking about a point, any point on the unit circle, on the boundaries, for example. So assuming I have very tiny one, a tiny bit, so which is the dx dy here defines the tangent vector, right? Tangent vector talks about a very tiny, I use blue color, right? A very tiny line. So this one is on the boundary. Okay, so I want to talk about how many particles coming in or going out for the tiny bit dx dy, which is for a little bit piece, right? I want to, so this is an integration of the very little piece of this. When you integrate all the stuff, you get the integration, you got the divergence over all the boundaries. Okay, now I cannot do this one time. The reason, the key point of this, I cannot do this. I cannot do the integration of c of my f2xy negative, this has to be f1 xy time dr, which means I cannot time dot product dr dx dy directly. The reason, because if I do this guy dot product this, I'm going to compute it. This is the same as I computed the projection of my vector field onto this direction, right? Because the particles along that direction doesn't move out. It still moves along the boundary. It doesn't move out, right? It's still within the region. If you consider boundary part of the region, it's still within the region. So this one, the divergence on for this piece, you really have to compute this vector field cross product the small vector perpendicular to this one, but it has the same length, but it's perpendicular to that. That tells about the divergence of this little piece. Okay, that's why I don't have this. This is not right. Okay, I have to calculate this. What I do is I have to first calculate another one direction called p vector. This p vector is perpendicular to my dx dy, and also I have to point out, the vector has to point out, because I cannot point it in, right? Point out, okay? What it means is this has to be dy over, this is the reason p will be given by dy negative dx, because if you do the dot product, it will be 0, because dx times dy plus dy times dx, this dot product will be 0. If dot product is 0, which means they're perpendicular. Okay. Second one have the same length, right? Yes. If you do the length, you swap this one. Yeah, the length will be, you put a negative. The length will be still the same. And also, you is pointing out because there could be, you could have two different p's, right? One is negative dy and dx. This is also perpendicular, but this guy, let me use another color. This guy, negative dy and dx. Now this guy is just pointing inside, okay? Because I'm caring about the divergence to the outside, so I have to do the use a dy times dy negative dx. That's why the divergence, the accumulated divergence at the boundary is actually calculated by this. Is the line integral of f2xy negative f1x. This is a vector field, and time, this is dy negative dx. That's the vector perpendicular to my dx dy. It's going to point out, right? And this, you integrate over this all the boundaries, which is the same as the integration over c f2 xy and f1 xy dy and dx. Of course, you can also swap the two. I do f1 and f2 dx dy. Okay, that's why it's the same as this. Okay, same as this, right? The reason because the accumulated divergence at the boundary is calculated by this. That's why here, this guy equal to integration of c and f1 dx. I do this one, f1 f2 dot dr. Okay, so that proves that, yeah, based on the physical meaning, yes, it does. What this Green Theorem says, the divergence of a vector field for some vector field for a region, a closed region, is the same as divergence only across the boundary. This is what the Green Theorem says. Okay. Or the physical meaning of Green Theorem. Okay. So now I'm going to show you one more example how to use the Green Theorem. Because in the previous example, I showed a very simple example how to use the Green Theorem to convert the line integral into a double integral, which is pretty straightforward to compute. Okay. Now here's another example. I show you how to use the Green Theorem to compute the line integral. This is not as easy as the previous one, but it still can show that the Green Theorem is very useful. Okay. So here I'm going to compute the line integral of c. So c is still a closed loop lines or curves, and of this function, this f is defined by x squared minus y squared and 2xy over dr. So my curve c is a boundary defined in counterclockwise motion. So it satisfies what we mentioned before, the Green Theorem of a region S. The region S is given by x from 0 to 1 and y is from 2x squared and 2x. So this line is basically 2x squared. This is 2x. So lower bound 2x squared, upper bound 2x. You can sort of say, hey, my x is between 0 and 1. My y is within 2x squared and less than 2x. So that's what we have. So this is what be the bound we use for the double integration, right? If you need to, okay. So of course you can also do this one. In order to calculate the line integral, you can also do this, right? Two components. You can do one piece over here. So this is my c1. This is my c2. You can decouple this as c1 x squared minus y squared 2xy and time dr plus c2 x squared minus y squared 2xy dr. Okay, that's also okay. I'm going to show you is you can still use a Green Theorem. Okay, so because the C is defined satisfies the condition, which means the region of S. Okay, this is region of S is on the left when you move along the direction of the integration of the line integrals. So which satisfies the property of the Green Theorem. So the integration over here is the integration of partial f2, the double integration of partial f2 over partial x minus partial f1 over partial y over the region S. Okay, so if we go back to the f2, so f2 is, so this is f1, this is f2 basically. So f2 is 2xy, so partial 2xy over partial x, I have 2y. Partial f1 is x squared minus y squared, so it's minus 2y basically. So if you do that one, this is what I get. So integration of that one, you'll get 4y times dx dy. Okay, so this is 4y. Next will be cancelled out. And which is the same as I do swap a little bit. I want to integrate over y first and x second, because I already have the region over here, because it's very easy to integrate over y first and then integrate x. Okay, when you do that one, you sort of try to split it into two steps. One is this is inner integration, this is outside is external integration over here. Okay, the lower bound, upper bound actually is already given. It was already given here, already given specified over here. So the y, the inner, as I mentioned for the double integration, so inner one could be a function of the external variable over here. So this is a function 2x squared is 2x. Okay, that's fine, perfectly fine. But the outside one must be numbers. Okay, so if you do the integration for the inner one first, so keep the outside to be the same. The inner one, integration of 4y over y is just 2y squared, and you value at 2x squared. Okay, and if you do that one is 2y squared, and y, you replace y by 2x, is 4x squared times 2 is 8x squared, and this one is minus 2, this is 2x squared is 4x to the fourth power times 2, so you 8 times x to the fourth power. Then we move 8 to outside. Okay, so we have only integration from 0 to 1 is x squared minus x to the fourth. Then integrate that, you have 8 times 1/3 times x to the cube minus 1/5 to the x, 1/5 times x to the fifth, and you value as 10, which is 8 times 1/3 times 1 cube is just 1 minus 1/5 times 1/5, 1 to the fifth is still 1, and minus 0 because there's a 0 over here is already gone. So it's 8 times 1/3 minus 1/5. You do the calculation, will be the 16 over 15. Okay, so that's final answer. As you can see from here, this is still relatively simple because you don't have a lot of computation. But if you do this way over here, we still have to follow the steps to find the parametric representation for C1, sort of xt and a yt, and also have to do C2. Okay, the similar ways, and you do the dot product and you calculate the integral. So this method is still relatively simple compared to the previous one. Okay, even if we don't have this guy is not a constant. This is not a constant. So it's still relatively simple. Okay.